current research focuses on structure and model-based RL, language for reinforcement learning and reinforcement learning for language, and as well as optimization and deep control learning of virtual and physical agents. So without further ado, let's welcome Roy.
Thank you. Thanks for the kind introduction and the invitation. Happy to be here. Imagining the crowds over Zoom. Hi, everyone. Do let me know if there's any questions. I'm hoping we can take some people over Zoom. But yeah, we'll start with this very long title. I realize it's long enough to make it into haiku, so sorry for the slight changes from as advertised. This rhymes better. The idea is that we're talking about foundation models. I'm sure you've all heard of them. But I'm a control person. I'm a reinforcement learning person. We don't have those for reinforcement learning. So the question is, what do we do with the ones we do? Let me start with briefly overview what those are, foundation models, just so that we're all on the same page. This figure is from a big survey of foundation models, big paper, very seminal in the field, describes what they are, what they can be, talks about what they can be, robotics as well, one day. So the idea is that they are trained on web scale data, trained from a lot of data, so they can be big models, and they can generalize well. And in fact, they can generalize for a lot of tasks that they were never trained for. Right? They were trained for maybe some prediction tasks or generation tasks, but then they can be used for a lot of other tasks downstream in the pipeline. To use them, you might want to take their intermediate features as embeddings and build some pipeline on top of that, or prompt them if we're talking about language models. By the way, vision models we can sort of prompt as well. With images, we can fine tune them, which might be hard to do if they're really big. So there's also adaptation, which is sort of if they have built into them these small modules that we can freeze the rest and adapt them, makes it a lot easier to do. I sort of underlined the three things we're going to do in this talk today. I'm not going to stop and say which we're doing, but we'll see. We also cover different modalities. So there's vision, language, there's speech. We're not going to touch that today, and many more. So hello there. Why not control? Why don't we have it for control? So it's sort of a big question, right? I mean, there's a lot of writing in that question, right? There should be a lot of value to that. There's a lot of value in these models. Vision and language, we're just starting to discover what they might do. Just imagine what it might do for controlling for robots, and for robots in more environments, in more tasks. We don't have them, so it's really important to try to understand why. I don't have answers. I'm just gonna, as a part of this little introduction, just gonna speculate a little bit. And so, big question is, where's the data, right? So what data are we going to use to train? We need big data. What's our big data in control? It's hard to come by. So maybe we deploy our learners, right, to collect data, like deploy the robot to collect more data from its own policy. That can be on task, right? So it's not from a different task. It's not from a different policy. It's on task and beyond policy, but we just can't collect too much of that. So that's not going to be big data. Use offline data, right? So big data sets that people collect over the years in many labs. There's more and more of those, very exciting, but there's a big distributional shift between that data and whatever happens when I deploy my agent, right? So in control, unlike many other domains, in vision, what I do affects the state of visit, right? So when I do something different than what they did in the offline data, I see different states, a different distribution of states. I might see states that I never saw in the data, and then really does my learning support what to do in those states? So that's a big question. We can have simulation to collect a lot more data. We have a lot of data from humans, right? Videos on YouTube of people cooking. Can you teach a robot to cook in those videos? there's a lot of questions there. The transfer gap is larger, so it's not easy to use. So a lot of people sort of say, okay, once we have this data, like we have in other fields, in other modalities, we're going to solve this. I think we need to go a bit deeper than that. I don't think that's enough reason for why we're not succeeding right now. We've been building these big models that really generalize across a lot of tasks. So here's a question, sort of to provoke that discussion. Don't we have the same issues in language, right? So we collect data from whatever humans generated speech, right? But then, or language, right? But then we roll out our own language generator. It's a little bit different. Doesn't it generate a different distribution of context than what we have in training data? Well, yes, probably, right? But does that matter? So I guess in language, it doesn't matter. Why not? We have better generalization across contexts. Is the fine tuning that we often do from human feedback that last touch that sort of solve this, right? And sort of make even more on task. Is that it? I don't think that's entirely the answer. Probably it's part of the answer, but I don't know. I think there's something more that we're not understanding about control. I think the state space is just so large and bizarre, much more than language, right? So if you think of the space of all contexts in language, in control it's a lot larger. What's worse is that in reinforcement learning, we're trying to optimize our control. We're seeking small data regimes. We're actually looking for those cases where they're hard for our offline learning, right? So we're sort of optimizing for things that might not have happened. So in lifelong learning, right, we're sort of the world changes, we're changing with it. Everything is non-stationary by definition. We have the same issue in language, but not to the same extent. In multi-agent systems, right, someone is optimizing for me to fail, right? If we're playing chess, right, when grandmasters prepare for a chess game, they're looking for those openings that are gonna bring their opponent into a regime that they are not familiar with enough, right? So they're actually looking for that small data regime, right? So that happens all the time when we optimize. And so I think that's part of the reasons for this is so hard. Okay. So what do we do? Well, let's use the foundation models we do have. Is there a question? Okay. Let's use the foundation models we do have. We have large language models, right? So people more and more are using those for control, right? You can sort of use them out of the box for control, right? Just for those tasks. So controller, maybe it's a robot, whatever agent, embodied or otherwise, could be virtual as well, is interacting with an environment by taking actions, taking observations, and sort of closing the loop of that control over multiple time steps. Why not do that in language model? So here's one example, sort of toy example that people have looked at to study this sort of domain. This is called Science World. I don't know if you can see it. This is just for illustration. It's not really what you see. It's purely in language, but there's sort of this agent walking around this lab kind of thing and doing stuff and interacting with materials and instruments and trying to do science, right? And so looking at the state of this world through text, through textual description of the state, then applying some text generation to generate textual actions that are then taken in this world, right? So the world, the simulator of the world can take in these textual actions, move the state forward and give it the textual state representation. Here's one example. So the task here is to measure the melting temperature of chocolate. The state is you see chocolate in a stove. Why is there chocolate? Well, for science, right? So the actor says, let's move the chocolate to the stove. Now the state becomes you see a stove with chocolate. Now the next action is you activate the stove. Then you see a stove with melted chocolate. Then you use the temperature, thermometer on the chocolate. The thermometer reads 40 C. and now you know the melting temperature of chocolate, right? That sort of interaction allows you to complete the task, right? That's just an example. So it's a purely textual world. Now, not all worlds are textual, right? We're really interested in the end in worlds that are not necessarily textual, and so we would sort of need to adapt to the real world, sort of translate between the real world and a textual representation if we're going to use LLMs as actors. And so, how would we do that? Well, in one direction, if we want to go from text to control, we would need to learn some sort of language condition skills. Usually those are low-level skills, short-term skills to just perform one step of that interaction, usually a small step. And so maybe we can train that with reinforcement learning, maybe with vision language feedback, right? So that's how we do the grounding. We see if we succeed in achieving the sub-goal that was set for that step, and that's how we learn from that feedback. Or maybe there's demonstrations, maybe from a human following the instructions, or the next step of the instructions to perform a task. We see those demonstrations, we can imitate that. Why does that work, or the general thing not work? Well, because it's such a short horizon, short-term task, right? So reinforcement learning is on this smaller task is a lot easier. In the other direction, we might go from observations to text by using those foundation models, right? So maybe a vision language module that can look at an image and describe what we see in text, right? So here's an example from a domain I'll discuss later, but this is a robot in our lab, and it's looking at a table in front of it, and there's all kinds of objects here, and there's a vision module that is sort of drawing bounding boxes around them, segmentation around these objects, and describing what they are in just a word or two of text. And then we can go for a state description that sort of describes the relations between these objects, right? Like the apple to the left and beyond of the ball, and so on, right? We can sort of describe the relations between these objects, right? Just programmatically from downstream of that foundation model. So maybe it's off the shelf, but we need to program some pipeline around it, or maybe we fine-tune it a little bit to work well. And essentially, we enumerate state features in text. That's essentially what we do. But are these tasks relevant, right? So one big problem here is that there are a lot of state features, right? The state is big, definitely when it comes to real-world tasks. There's a lot to say about this, right? Are we going to say everything? That's going to be a big context. That's going to be hard for language models. It's going to be very distracting. So here's one thing we try to do. Task relevant state summarization, right? So can we take that textual state coming out of maybe it's a directly textual environment or a vision language module and summarize it so that we don't need to work with the full text. If we do work with the full text, right, so here's another environment. This is called NetHack. It's this sort of weird game in the grid world. With this character, there's all kinds of things happening here. It's roguelike, if you know what that is. So the task is to pick up and wear a robe. Here's a robe. In the state description, well, it's long, right? Here's some of it. You have a club, you have a potion. Your position is 37.9. You see a rope right near east. You see stairs up adjacent to southwest, and so on and so forth, and so on and so forth. If you try to go from this context to now, what should I do? Well, one LM actor said, drink the potion. It does not compute. It does not get you any closer to where the rope, right? If you drink the potion. Why they say that? Well, there's so much distraction here. Who knows, right? Who knows what signal they thought they're picking up on? You have a potion, seems like a good thing to do, to drink it, whatever. So long context takes a long compute, right? So that's one issue, is that this just takes a long time. Also, there's a lot of distraction there, so it's error prone. We'll pick up on some random signal and do the wrong thing. So we want to do text-dependent state summarization. Right? So we want to summarize the state in light of the task, so that we highlight those features of the state that are most relevant for the tasks. So we call this blinder. It has some acronym in mind, but it's sort of a blinder on the agent that says, well, your task is to pick up the word robe, and the state description is you see a robe very near. So that's really all you need to do, right? All you need to do. And then the language actor can say, okay, we're going to move east as a first step. That's a lot easier. So we filter the most relevant state features, and then we have an actor that's a lot faster, a lot more robust to noises in your state, to variations in your state that may be irrelevant for the task. One nice feature about this is, right, so remember that we're training those LLMs from a lot of data. But that, all that data is irrelevant for our task, right? Well, maybe NetHack, it has seen on the web somewhere, but it's not relevant for this specific task, right? And it may be relevant for the environment, the future environments and weird environments, right? It's not directly relevant to that, or maybe it's supported by the data, but it's sort of a weird edge case that it's not really optimized for. But if we can take some on-task data and use that in addition to language model, now we have hopefully the best of both worlds. We have big data that informs our ability to read language and answer intelligently and sort of think sort of rationally or maybe even introspectively about what we're doing here, but then some on-task data that informs us about what really matters for those tasks. So here's some more detail about how this works. So the LM actor here is going to be frozen, it's going to be fixed. What we're training is only the blinder. The blinder is another language model. It's a summarization model. So it starts with a language model that was already fine-tuned to be a summarization model, and we fine-tune it further using reinforcement learning, essentially. Where the reward here is the probability of our downstream language actor to take the correct action. So we start by collecting some demonstrations, successful demonstrations of the task. We don't need much. We need, in this case, just 5 demonstrations of the task where the actions are correct. Then we're saying, okay, so what's the probability of the language actor to take these correct actions? And we get a reward for doing so. And so we can now look at our expected future accumulated reward from adding one feature into our state features. Right? So the value of a set of state features for a task is something we can learn now from this data. And the summarization works like this, where we're adding more state features, the one that's most valuable, as long as the one that is valuable, that adds value to our estimated value function. So that's blinder. So reinforcement learning for language for reinforcement learning, which is kind of cool. Let's see how well it works. Yeah.
If you compare it to just using data to fine-tune the language model, you will presumably a lot more.
Yes, yeah. So fine-tuning the language model itself, the actor itself, is not going to work. Definitely not from this little data. It's not meaningful for that, right? So that structure that we're adding here, predicting how well it's going to do, that is what it's going to do the trick. Another thing you could do is not fine-tune the actor, but prompt it. That we actually tried with a few shot prompting of the actor, and that's not working as well either. I don't have the figures here, but it's not working as well. So we experimented with this in 2 domains, NetHack, and this robot we have in lab. It's called Stretch 2. It has all kinds of sensors that we use behind the scenes for low-level control, but for what matters here, we have an RGB camera that we're putting at the table that we're looking at and capturing those objects, describing them in text, and that's our raw state representation. So what we can see here, we're comparing four things. On the NetHack environment and the robot environment. The x-axis is the average description length, right? So how many state features do we have on average after summarization, right? So the less the better, right? So go to the left is better. This is log scale. The y-axis is success rate at the task, right? So ideally you would be left and up, right? So very compressed state, very succinct state, and then very successful pipeline. So we're comparing four things here. Black is with the entire full state description coming from our vision language model. So you can see that these are very long descriptions and often not very successful because they're distracting. I'm not even talking about the compute time. This is just how successful it is. Then we can try off-the-shelf summarizers. So there's two that we're trying here, T5 and GPT 3.5. T5 is a smaller model, so the size of the circle tells you how many parameters it has. The area is proportional to the number of parameters. So T5 is a lot smaller, and so a little bit less successful at the task, a little bit more compressive though. But GPT 3.5 is a huge model. It's going to be a little bit more compressive than our method, but we are a lot more successful on that hack and a lot more compressive on the robotic tasks. So generally speaking, we are better, at least in some trade-off than baseline. Now we can ask another question, right? So we can ask, okay, so we fine-tuned our own language model to be a summarizer. Now, are we sort of tied to that, or can we change the actor? Do we need our summarizer and actor to use the same language model? And the answer is no. We can switch the model of the language model of the actor and generalize to different ones just the same. So we trained on a T5 actor, but we work just the same on a GPT 3.5 actor. So that was one thing we could do. But that doesn't seem enough, right? So what have we done here? We sort of filtered our context. We sort of narrowed it down so that it's not containing bad things, but does it contain all the good things, right? Can we enrich it? Can we have more? So now that we subtracted things, let's add things. What can we add to our context that would help the actor? Remember, we want to use our on-task data that we collect for a specific task to enrich our context. So here's one question that we can ask, right? In the context, when we have some experience in the task. What am I doing here? Is this anything like things I've done before, right? That's sort of the natural question for generalization. So can we have that kind of generalization? Let's see what that looks like. So here's the task from before, melting chocolate. There's another one here, measuring the melting temperature of water. And the state is you see a stove and a freezer with ice. What does the LM actor do in this case? Use a thermometer. Well, that's not the right answer, right? You take the ice, put it on the stove, and so on. For some reason, it's not doing that, right? It did not generalize well. Maybe this is so common that it just had a shortcut and thought that's enough. It's not aware that it's controlling the thing, right? It's just generating language. But here's another thing we can do. We can look at this previous experience that we had, melting chocolate, and maybe melting other things as well, to measure their temperature. And we can feed it into our algorithm that I'm going to describe in a moment. And then we can come up with some commonality, some sort of pattern here. The pattern is melt a substance, you move the substance to the stove, reactivate the stove, right? There's sort of a principle here that we can discover. if we have that principle in our context, together with the task and the state, now it's a lot easier for the actor to say, okay, you know what, I know, move the ice to the stone, right? I sort of see the template, I can instantiate it for the water, for the ice in here, right? So it's a lot easier. How do you come up with these generalizations? We want to identify behavior prototypes, call them skills, right? There's different things called skills. In reinforcement learning, we'll call these skills. And then that adds structure to an actor's execution. So you can sort of think in terms of higher level abstractions. So there's a sense in which once we move from low level control of motors and so on to language, we're already at some abstraction, right? At some higher level of thinking about the problem. But we're going to move into a higher level still, both semantically and temporally, right? So we have temporally extended actions, and that's going to help our generalization. So here's how it goes. We start with the interaction, right? So we have our so we have the environment. It's producing a state for us, and now what we're going to do is we're going to use that state to look at the skills, a set of skills that we've trained previously. I'm going to say how in a bit, and we're going to retrieve skills that seem relevant for our current state. So we're going to retrieve maybe 1 or 2 up to 3 skills, and then we're going to put them in the context of the language model actor when it comes to choosing action. And that's going to be a lot more, that's going to be very helpful in choosing a good action to control the work. After we do this for a while, so maybe we perform the task a bunch of times, we collect those trajectories. Now we take those trajectories and we can do skill set construction. I'm going to say what it is in a bit. And then afterwards, we can also look at what skills we actually executed and do some refinement of the skill set. So let's see what these are. Construction. So construction has 4 steps. First, we look at the trajectories that we collected. We look at the pairs of them. And we're looking for commonalities, right? So where the embeddings, the textual embeddings of the states follow a shared sub-trajectory for a while, right? So it's the diagonal here, right? Where the 2 trajectories have high correlation for a while. So those are sub-trajectories that are highly correlated, right? They seem to follow a similar pattern semantically. Great, so once we have those identified, we take a sub-trajectory and we extract rewards and similarity and length scores for it, sort of to see, is this a good candidate for something that really generalizes? It needs to give us a high reward, otherwise it's not worth it. It needs to be really similar to another thing, and it needs to have some substantial length, not just 1 step or 2, so that we can actually have this temporary abstraction. And then now we can sort of sample from these sub-trajectories, and what we need to do is summarize a collection of sub-trajectories to find their commonality, to find a skill which we define as a sub-goal in a list of instructions to reach the sum. Right, so the skill, it says, well, you know, in this state, you might be able to reach this sub-goal if you follow these instructions. Right? So that's a representation of skill that's going to be very useful for language model. Now, once we have that skill set, what we can now do is refine it, right? So it's too easy for not so useful skills to make it into that skill set. Let's take them out. We just see that they were not really used in high value trajectories, and so we sort of throw them out. And make room for others. And so let's see some examples just to see what it's like. So in science world, for the melting temperature task, a subgoal might be the stove is turned on. On the stove is a substance called liquid X, right? That is our subgoal. That's what we're going to reach. And we might do that with focusing on the thermometer, focusing on a substance we want to heat, moving it to the stove and activating the stove. That gives the language model the correct level of instructions to follow when it comes to do that something. In the NetHack example, maybe we want to unlock the door, so we need to stand by the door, use the thing that unlocks the door, and then when it asks us, do we really want to do it, we say Y for yes. That's just the interface of NetHack. And now you can see in rows here, you can see different skills that we're learning. And along the row, you can see in which iteration it was used, right? So a skill can only be used, of course, after it's been discovered. And you can see that as time goes by, we're sort of discovering better and better skills, more useful. You can sort of see that, at some point we discovered that we can go to the kitchen and activate the stove and so on. And you can see it vertically that we tend to be using more recent skills, right? They're just more useful than previous ones we sort of got rid of. And so now, compared to some baselines, I'm not going to describe too much, but also baselines that use language models with some memory structure as well, we see that we just learn much faster from the same amount of data. We learn a much more successful execution. And here in green, there's Science World, and in orange, there's NetHack, just to show you the improvement over time, how the size of the skill set grows. So we're finding more and more skills that are worth keeping. How the number of skills that we're actually using in our execution goes up gradually, but does go up. There's a caveat here, which is these are the skills reported by the language model being used, right? So it's hard to know what skill was actually being used when they're all in the context and what is actually relevant for the action selected. So we asked the language model, what do you think is relevant here? And this is reported from what they're saying. So it might not actually be true. And the task score also gradually goes up, and we probably keep going up if we do this for a while. Any questions before we sort of move on to the next part? Yeah.
Yeah. When you state changing, do you add new skills to the skill set?
Yes. So as we collect more trajectories, we might discover more skills, more commonalities between them. We add them to the skill set. At the same time, we evacuate those that have not participated for a while in successful trajectories. Good question. All right. So, okay, this is cool. What more can we do, right? So, in a way, this is nice that we can enrich the context of the language model. It's not really doing something fundamentally different, right? There's a big trend these days in reinforcement learning, doing model-based reinforcement learning. Some algorithms that achieve some great breakthroughs. There's a lot of excitement about the ability to learn models, right? So intuitively, we would like to learn world models because they generalize better, they transfer better, they're more robust. If we can pull it off, which has been tricky before, but now we have some better algorithms to do it. So can foundational models help us do that? Well, they carry information about the world. That's why they're useful, right? They carry information about state transitions and valuable actions, what are the valuable actions, right? We saw how we might go about extracting that information, but that might not be enough. So that information is not specific for the task. It's not a task. There may be information missing that we need for the task if it's not there. We won't ever said anything about it on the web. There might be misleading information, contradictory information, right? From other contexts where things happen differently or irrelevant and confusing. So you should not just trust the model of the language model likely. Instead, what we can do is use it to guide our own learning of a world model. So we're going to do on-task learning of a world model guided by a foundation model. This is a scheme of a recent successful model-based reinforcement learning architecture. And so what we can do, right, with language, we started by having language here just for the interaction. That was the actor. We add the language here, right, in the context of the actor. And now we're going to add language here in learning a model that informs learning the policy to control the world. We're going to take it all the way through. Let's see how to do that. But I should say not just language. So actually, I'll start with vision. So let's see what this scheme is that we're building on. It's called Dreamer. It learns a latent state representation of the dynamical process by looking at the reconstruction of observations. Right? So we're reconstructing observations, we're predicting rewards, and we're predicting the next state, the dynamics of this latent state process. And we do all of it at the same time. So this is what Dreamer looks like. We take the observations, we encode them into a latent state where we can predict rewards. We can also predict the next state if we have an action, right? So we know the dynamics of the world in this latent state. And we can also go from this latent state back to the observation by reconstructing the observation. But I should say, when we actually use this to learn, to use reinforcement learning, we need the rewards, we need the transitions, right? It's kind of like an MVP. What about the reconstruction? We don't actually need it for the reinforcement. It's an auxiliary task just for learning this latent state. Okay. So it's an important auxiliary task, right? People found that you have to have it. If you don't have it, there's not enough signal in just the reward prediction over time to learn this latent model. So observation image reconstruction helps a lot. But what if there's some distractions there? So, what if there's part of the observation that is not relevant to the task? It's going to be detrimental, right? It's going to be distracting. It's going to take away our presentational power. It's going to take away our learning power, right? We'll find spurious correlations, right? That we don't want to find. Can we have a foundation model that does visual segmentation to focus on the part of the observation that is relevant for our task? So here's one foundation model. I'll go over it quickly. It's called personalized SAM. And so what you do is you give just one shot example of an image and its segmentation, its mask. Either with training, without training or with training, you then build this personalized segmentation that can very quickly and very successfully segment that specific thing that you thought was important that you said in your example. Right? There's a personalized SAM, and there's personalized SAM F that actually does a little bit of fine tuning of just two parameters very quickly, 10 seconds, and it has superior performance for segmenting the thing you said you care about. Can we use these to segment things in our visual control task that we care about for the task? The idea is this: we're only going to reconstruct, to learn a reconstruction of the masked pixels of the segmentation, right? Not of the things that are outside that segmentation, right? So presumably it highlights things we care about, and we're only going to learn to reconstruct that. So here's another view of Dreamer, right? We have here the input, we have here the dynamics, and we have a decoder. Now, how do we train a decoder? What's the loss here? Originally, there's a loss from the actual input. We need to reconstruct that again. You see here an example with distracting background, right? So we just place some random video in the background of this walker task, and it's very distracting, right? So the representational power of Dreamer is going to focus on those pixels that don't actually matter for the control. Alternatively, if we have the ground truth mask, we can just apply that mask and only reconstruct that part of the image. So that's going to be again task relevant and filters away the distracting part. Now, if we don't have the ground truth, we can use personalized SAM to approximate that. And this is an exaggerated bad example. Usually they're not this bad, just to show you the difference. Usually they're pretty good. So we can do any of them. But here's a question. Why are we masking the reconstruction and not the input itself? That's actually been done before. Why is it not as good? Well, there's many reasons. One is this way we save compute, right? So we don't actually need to apply it to the input. We don't need to apply the masking to the input at execution time, right? When we roll out the agent. So we save compute, right? We deploy the agent, doesn't actually need any simplification. It's just in the training of this observed task. We can also be more robust to mask errors, right? So imagine if we had the mask error and we apply it to the input. Now we'd be missing some of the input. We'll see an example of that later. We may have a ground truth segmentation, right? Maybe we're training a simulation or for some reason, that might be a reason why we have the ground truth. And that's another reason to use it only for the reconstruction so that we can use it in training and not need it. Otherwise, we can use a foundation segmentation. So let's see what this looks like. So we're going to try these 6 tasks, simple control tasks from vision for pixels. We're going to add this distraction here. This is a ground truth segmentation, and this is what personalized SAM does. Pretty good. Now here's a question. Do we really want to look at exactly the predicted mask? Sometimes it's a little bit off. Not often, but sometimes. When it's off, it's hard to predict that it's going to be off, right? So our reconstruction is not going to know that this is bad, right? It's going to try to do the right thing. Now there's a mismatch. So if we just apply a loss between them blindly, we're going to have a high loss here, although this is doing the right thing. So we don't want to do that. Ideally, what we want to do is we want to look at the ground truth mask and say, okay, you know what? You got the pixels right where it matters. Let's not penalize it for those pixels that it got right where it matters. So black is where we ignore the loss. We only compute the loss on the white. We ignore it where, yes, it's outside the mask, but the pixels are right, so it's fine. Ideally, that's what we would like to do, but we don't have the ground truth, so we do something approximate. Essentially, we look at the prediction, and we look at where the pixels match the input, which we do have, and there we sort of filter out the loss. We don't compute the loss there. It's a good approximation of what we really would like to do. And so here are some results. The dashed blue line is just Dreamer without distractions, right? So ideally, the best thing to do. The green line is Dreamer with distractions, just vanilla Dreamer. You see that it's pretty bad everywhere, right? It just cannot handle the distractions. With our segmentation model, so with the ground truth, we almost always match Dreamer without distractions, but we match it with distractions. There's one case where we don't, and in the interest of time, I'm not going to explain why, but there's a reason why we can't do that here. There's an alternative formulation which we can. And with an approximate mask predicted from this foundation model, we get pretty close. Not always, but usually pretty close. The interesting thing is, one of the interesting things is that no previous work ever was able to do sparse rewards from distraction. So when you have a very sparse reward signal, it's hard to recover from those distractions. And we're the first, to our knowledge, work that can actually operate under distraction in sparse rewards. And we beat other baselines and other benchmarks as Um, this is just quickly why we need selective L2 loss. You can see that it improves recall without hurting precision too much. But I do want to have, with the little time I have, to talk about the last part, which is backward language, vision and language. And we're going to build world models, but this time abstract world models. So what do I mean by that? So the same way that we've now ignored pixels, we really want to ignore low-level aspects of the dynamics that don't really matter, right? We want to focus on the high-level things, the long-term things, the long-term predictive, value predictive features of the state. Presumably, right, we can always recover from that abstraction by looking at the low-level set of skills that are myopic. They don't need to look long-term, you know, their long-term implications and value. They only need to perform short sub-goals. Because they're so myopic, it's easy to optimize. Right? We've done that before. Presumably, we can do that again. And so it's good to abstract away from those low-level skills and think in the higher level using the abstract word models. So here's an example in a domain called Minecraft. I'm sure you've heard of it, right? So the agent is behaving here in this world, controlling from vision from these pixels, and it needs to construct a pickaxe, right? So maybe it needs to collect log, then make planks, make a table in a stick and a wooden pickaxe, and then maybe also gather cobblestone with that pickaxe. And finally, you can make a stone pickaxe. This is our task. It's complicated. It's hard to train it with just reinforcement. So here's what we're going to do. We're going to have a hierarchy. The high level, the low level is going to be this is a VPT is a video pre-trained, so it's sort of another foundation model, but it's pre-trained to perform low-level skills in this visual control task. The high level is going to be a language model that is going to tell us what this graph might look like and sort of guide us through the subgoals. So let's see how we generate it. We're really going to brute force it, right? So we're going to feed this prompt into this big language model and ask it, can you please, in this very structured language, build this graph of what it might look like to make a stone pickaxe? What are the steps towards that? Can you tell me what quantity of items I need and how to put them together to make a stone pickaxe? And so it outputs something like this, right? This is the abstract word model that predicts. There are errors here. It's not all correct. There's 35% of the items are missing some dependencies. There's some added dependencies and some wrong quantities. But it's not as bad on common items that presumably appear more in the training data. The point is that we can recover from that, right? We're not just going to use the language model. We're going to use it to guide our exploration. So here's how it works. This is what was proposed by the language model. And so we're going to pick a node, maybe the first one, because that's the one we can reach. So gathering in log. And we're going to go out to the world, take some episodes where we explore and try to actually fulfill that subtask. Eventually, we'll be able to collect log, right? With this pre-training, it's not going to take too long. So this goal is verified, right? We verified that we can do it without any prerequisites. What about planks? Can we do that now with logs? So we're going to go out, we're going to collect logs first. And now can we make planks? Well, if we succeeded, then yes, now it's verified, and so on. And there's actually going to be a mistake here, where we cannot make this wooden pickaxe just from planks. We need the table and the stick. So we falsify this hypothesis of the language model. But there's another one that we can discover, and so we can recover and make this pickaxe, and so on and so forth. And so let's see how well this does on some tasks in Minecraft to make some various things. So in blue, we have the pre-trained model, right? It's pretty good, but it's not really achieving a lot of success on most of these tasks. But now what we're going to do is we're going to fine tune it with reinforcement learning, just exploring the world and trying to do better in these tasks. And we're going to do well in some of them, but some of them that are deep in the production tree are going to be really hard. But if we have a language model that suggests this sort of structured exploration roadmap, we're going to be able to do a lot more, and even some of the really hard tasks like glass that takes 8 subgoals. And we see that our agent in green is able to find those subgoals a lot faster than the baselines and with fewer rollouts. All right, so to summarize, foundation models are really powerful. We know that. Maybe too powerful, maybe too soon. Not going to get into all those societal questions. But we're going to look for them just the same, even for control. Hopefully, we have regulation in time to save us from the bad AGI. Are they coming from control? That's a big question. I'm not going to risk guessing. My guess is that not soon, but I wouldn't really be surprised if they come out next week. It's possible. But I do think that there are big challenges ahead that we're not yet facing. And so in the meantime, we can use those foundation models we do have to improve our control. And with that, I'd like to thank all my collaborators, particularly Kobe Nottingham and Kevin Kim, my students who did most of this work, and Samir Singh, who collaborated on this, and a lot of people from the Allen Institute. And thank you. Any questions? Yeah.
I wonder, like, a more general question of like, what do you think those foundation models can be used in some application, like the safety critical control, like if the robot is operating in some dynamical changing environment and it needs to, based on its sensor data, to make rapid actions. If those models are too large, it cannot be deployed on those mobile robots. Or if you need to communicate with a crowd, it may take too long. So yeah, I wonder if you have any thoughts on those.
For sure, yeah, good question. I thought you were going somewhere else with this. So I think you were saying two things. One is that there's the challenge, sort of the technical challenge of actually providing that information in time for the task, right? So if we're waiting for input and we need to do something in between, right? How do we maintain safety while we're waiting for these language models to resolve? That's one question. I think that's the easier one, right? So a lot of these tasks are not actually time critical. We can take some time to think, right? Definitely, if you're thinking of deploying robots in the home, for example, or in hospitals, not surgery, but just as helpers, right? Service robots. It's not the worst thing if they need to take a moment to think about what they're doing. We probably should for safety. So the harder thing, I think, is if we're going to rely on these language models, they're sometimes wrong, right? So for safety, right, when you talk about safety and control, you need good priors, right? So definitely if you want to avoid ever trying those risky things to find out that they're bad, right? You don't want to push the button to discover that it was a really bad thing to do. So you need a model that says this is going to be bad, don't do it even once. It better not be a language model trained for some other thing that you're just repurposing for this. It may be wrong. It will be wrong a lot of the time, right? So I think there's the hope of using some of these ideas where we're not relying on the correctness of the language models. We're just relying on them for hints to accelerate our learning. But in the end, we're doing the learning ourselves. And then we can fall back on some other techniques in safe reinforced learning. That is a challenging field, but has some answers.
Thank you.
I have a question. So, how do you define the word model? Because I see there is a graph for the Minecraft domain. That seems to be a topological constraint between those scales or tasks, which is a little bit different from the definition of model with RL. So, what would you think?
Yeah, so it's not that different. The only thing is that it does not resolve all the way to the actual environment. So a model is usually, when we say modeling RL, we mean essentially the dynamics of a state, maybe also a reward function, if that's not given. When we are trying to model the actual world, we do that at the low level, at high fidelity, and trying to capture the actual dynamics of the real state. In an abstract world model, we're trying to abstract away from that, so it's not going to capture the real dynamics, but it is going to be some dynamics, right? So that graph is, you can take actions that move you from one node to the other, right? So if you're crafting planks, you've moved from having logs to having planks, right? So there's some abstract action that moves you from one abstract state to another. So in that sense, it's a world model, but it does not resolve all the way, right? There's still some work to do to say, well, how do those actions translate to actual actions? Does that answer you?
Yeah. Maybe I think another question is that so we mentioned that a key feature for the word model is that it should be very general, but in your work, maybe you have this kind of abstract work or representation, which seems to be a little bit hard to transfer between different environments. And on the contrary, maybe if we have a general model, like for video generation, like the Sora from OpenAI, they also claim it's a word model. It seems a pixel space, as you said, there's going to be a lot of distraction or irrelevant information. Yeah, so I want to know, what do you think about the future? What the word model should like?
Yeah, good question. So I can see the point that abstracting may limit generalization, although the idea usually is to generalize different tasks. You're right that there's also the question of, do we generalize to different dynamics? And I would propose that more often than not, abstracting actually helps to transfer and generalize across slightly different dynamics. So one of the things we're currently using world models for is sim to real, so transfer from simulation to reality, with the idea that if you learn a very accurate world model, a very low-level world model, and now something slightly changes about your environment, right? So maybe you got the friction coefficient slightly off, or the mass of the arm, or whatever, slightly off. The whole dynamics may be off now, right? Over one step, it's not too much, but it accumulates, and the predictions long-term may be off. But if you abstract to a high level, right, and maybe you fine-tune the low level, which is easier, you may generalize a lot better, right? Because you're saying, okay, when I'm going to grasp this object, it's going to be in my hand. That's still true, regardless of what my mass is, right? So if you abstract enough, I think it generalizes better. But what is that enough? It's an open question. Good question.
There are no other questions. Let's